Good morning, students. My name is CH.S.V.PRASAD. I am working as senior lecturer in EEE department in Government Polytechnic Yadirkutta. Today I am going to start AC motors. In AC motors, we will start synchronous motor chapter. In this one, last class we covered principle of working of synchronous motor. So that means how the synchronous motor will work. So last class we explained with the figures. We considered a synchronous motor with a two-pole winding and the stator is three-phase. It is connected. When a three-phase supply is given to three-phase stator winding, then a rotating magnetic field of constant magnitude is produced. Assuming the stator is producing a poles, that is north pole and the south pole, which is rotating in a synchronous speed. So similarly, the stator also produces, when we give the excitation, the stator also produces poles, north pole and the south pole. But in first half cycle, the poles are north pole, south pole, and both are same. That is, the north pole of the stator and the south pole of the stator are in the same direction. As we know, the like poles repel each other. Due to this phenomena, the rotor tries to rotate clockwise direction. But before the rotor reaches at 50% of the rotation, the stator magnetic poles also changes its direction. That is, north pole comes at south pole and south pole comes at north pole. Then automatically the rotor pole is reflected and again it rotates in anti-clockwise. Due to this clockwise and anti-clockwise rotation, it produces a torque that is called pulsating torque. Because of this torque, the motor is not going to produce a forwarding direction and it is not possible to rotate. So this is the reason why synchronous motor is not self-starting. So how we can make the synchronous motor self-starting? So when three-phase supply is given to three-phase stator winding, a rotating magnetic field of constant magnitude is produced. We derived in the last class the resultant flux of this rotating magnetic field at any angle, that is 0 degrees, 45, 90 degrees or 150 or at any direction. The resultant flux is constant, that is 1.5 times of the maximum flux, and it is rotating at a synchronous speed. What is synchronous speed? That is the rated speed of the motor which is rotating, and it is denoted with ns. So that is ns is equal to capital N and suffix s, that is called synchronous speed, and its formula is 120 f by p, where f is the frequency and p is the number of poles. So when a three-phase supply is given to three-phase stator winding, it produces a rotating magnetic field and it rotates at a synchronous speed. So how synchronous speed? The stator poles rotates at constant speed. That is the magnetic poles. So to make the motor to start, so what we have to do? We have to rotate the rotor also near to the synchronous speed by using some external means, by using some any DC motor or small AC motor. The rotor winding, when the rotor is bring to is near to rated speed, the rotor winding is switched on to DC supply. Then the rotor poles becomes powerful electromagnets like stator poles. As these both are rotating in the one same direction, the stator poles and the rotor poles attract each other and starts to rotate in the same direction. This attraction is called magnetic locking. That is, the stator pole and the rotor magnet pole is attract each other. This is called magnetic locking. When both are get magnetic locked each other, they starts rotates in the same direction. So this is the method how we can start the synchronous motor. So if you see the characteristics of synchronous motor, it is a constant speed motor and it can be operated at any power factor, that is leading or lagging power factor, and can be used as a synchronous condenser to improve the power factor in industries. So this is the thing what we covered in the last class. Today we will check performance of synchronous motor on load with no losses. That is the ideal synchronous motor, and performance of synchronous motor on load, that is with losses. And next, synchronous motor on load, how the synchronous motor performance changes when we have connected load. Analysis of phasor diagram, how the phasor diagram changes. So synchronous motor behavior on load. When load is increased on DC motor, what happens? Its speed is reducing. In DC motor, not only the speed is reducing, it produces a back EMF, EB, where EB is called back EMF and it is denoted with a capital E and suffix small b. So where EB is equal to 120F by P and it opposes the supply voltage. So this resultant voltage across the armature is the difference between supply voltage and back EMF EB. So the voltage across armature is V minus EB. So if you see the armature current, so then what is the armature current? Then armature current is the armature voltage by armature resistance, where RA is the armature resistance, back EMF depends on the speed, but in synchronous motor back EMF is set up in the stator. The back EMF depends on the excitation given to the field only. That means how you give the excitation, if you increase the excitation or change the excitation, and depending on that one, the back EMF is changes. It does not depend on the speed. So why in synchronous motor the speed is constant? That's why it is independent of the speed, where EB is equal to pi p and z by 60A. Similarly, DC motor armature current of a synchronous motor is given by IA is equal to V minus EB by ZS, where ZS is equal to synchronous impedance and V is the supply voltage and EB is the back EMF, which depends on the excitation, and it is not and it is independent of the speed, as the speed is constant. And synchronous impedance is the combination of armature resistance and synchronous reactance, where Ra is equal to stator resistance and Xs is equal to synchronous reactance of the stator and V is equal to supply voltage of the synchronous motor, and where Eb is equal to back EMF of the synchronous motor. So synchronous motor on load with no losses. When the motor is running on no load with field excitation as shown in figure, it is assumed no losses. That is, the magnetic locking between the stator and the rotor is that in such a way that the magnetic axis of the both will be comes on the same plane as same axis as shown in figure. That means both the stator poles and the rotor poles comes on the same axis. So what about there is when there is no losses, the back EMF is equal to supply voltage and both are in opposite direction. Then armature current is 0. So why? Because the vector difference between V and Eb is equal to 0 and both are equal and opposite to each other, where V is equal to Eb. So armature current is 0. That means the voltage across armature is 0. So armature current is 0. So this is called normal excitation. When armature current is 0 and supply voltage is equal to back EMF is called normal excitation. As shown in figure 2, both EB and V are equal and opposite. Both are at 180 degrees phase displacement. So motor takes no power as there is neither load or losses. When there is no load and no losses, then what happened? It is a ideal motor and it is not going to take any input also. But motor has to supply mechanical iron losses along with small copper losses. So practically every motor has the losses. So previously it is showing when EV is equal to V, when there is no losses, that means there is no iron and mechanical losses or core losses. At the time EB is equal to V and armature current is 0. But practically every motor has losses. When synchronous motor running on no load with losses, the magnetic locking exists between stator and rotor poles. So, but these exist a small angle of difference between the two axes, that is magnetic field. The two axes, that is the rotor axis and the stator magnetic field axis, both are not in the same plane. Both they will make at a phase difference of a small angle as shown in figure. So this is the figure which shows the synchronous motor on load with losses. So if you observe here, there is a phase difference between the axes. So when it has the losses, you can see here clearly this A and B shows the stator axis, whereas the rotor axis is making at an angle of alpha. This angle is called load angle. This angle alpha decides the amount of current to be required to produce the torque which bears these losses. This angle is called load angle or power angle or coupling angle or angle of rotation. So that means when the load changes or losses changes, the angle also changes such that it develops a torque which supplies the increase in load and increase in losses. This angle alpha is called load angle or power angle or coupling angle or angle of rotation. Angle of rotation. This angle, for every change in load, the angle alpha goes to a new value and it develops a torque which supplies the output and the losses. So though EB, so this is the vector diagram with losses. It shows the alpha angle, the angle between voltage and EB. This is the alpha angle, and the angle between resultant voltage and the armature current is called theta. And the angle between voltage and armature current is pi. This is the shows the figure vector diagram where it contains back EMF, resultant EMF, and supply voltage. So the vector difference between EB and V is not zero but gives rise to a resultant vector ER. What is ER? ER is a combination of back EMF EB and V. If we joined back EMF V, EB and V vectorially, we will get a resultant vector, which is nothing but a IA into ZS, where IA is the armature current and ZS is the synchronous impedance. So the resultant decides the amount of armature current, either it and which produce the torque, which, which produce the torque, and which is the torque supplies the load and the losses. Suppose if we apply the load on this one, again the angle alpha changes and it develops a torque which supplies these losses. So armature current is called ER by ZS. Under no load condition, alpha is very small. Why? Because if it has only uh, iron and mechanical losses and there is a small core losses. So ER is very small. As shown in figure, the current drained by the motor is very small. When the motor, synchronous motor is on load, as the load on the motor is increases, alpha is increases. But there is no change in its speed. Why? Because the speed is constant. So as alpha increases, the resultant vector ER increases. When ER increases, the current drawn by the motor also increases. When armature current increases, then it produces a torque which is sufficient to meet the demand. So that means when the load changes, automatically The alpha changes, resultant EMF ER changes, and armature current, it draws more armature current, and then that draws more torque, and that torque supplies the applied load. So whereas the back EMF depends on the excitation, how much excitation we will apply on the motor. So this is the vector diagram when the motor is on load with losses. Once again I am repeating, when the motor is on no load with no losses, then what happened? Then both the vectors, that is the back EMF and the supply voltage, are equal and opposite. So the armature current is equal to V minus EB, that is the armature voltage. So the armature voltage is 0. When armature voltage is 0, automatically armature current is 0. Then it is with no losses. That is the vector difference is 0 and the armature current is 0. This is called ideal transformer. Hence the motor is said to be floating as there is no input and no output. But in practical, every motor has a losses. The vector diagram is shown here. This is the vector diagram. The vector EB falls back by a certain angle, that is called alpha. This is called load angle or coupling angle, as the rotor and the stator poles engagement is not absolutely rigid one. From vector diagram, it is clear that resultant voltage ER and hence IB brought into excitation when it has the losses. When the motor is loaded, when the motor is and this is on no load, that means when the motor is on no load, it experience produces the torque which is sufficient, that is the angle alpha angle changes so that it supplies the losses of the motor. When alpha changes, automatically the ER also alpha increases, ER increases. That is the resultant voltage increases. When resultant voltage increases, it draws more current from the supply. This current produces more torque and which supplies the increased demand. So when the motor is on load, the rotor progressively pushes to a new value of alpha. The rotor progressively tends to fall back in phase by angle alpha. That means the angle changes to alpha, but still the motor continues to run at a synchronous speed only. The value of load angle depends on the amount of load to be supplied by the motor. As the load increases, the alpha angle also increases. When alpha increases, resultant voltage ER increases. When ER increases, armature current IA increases. When IA increases, automatically it produces more torque, and this torque supplies the increased load which is increased. But the motor runs at synchronous speed only. So why? Because the magnetic locking still there between stator and the rotor. So this shows the vector diagram when the motor is on load. So see here the alpha angle is increased When the alpha angle is increased, ER is increased. When ER is increased, IA is increased. When IA increased, torque increases, and that torque supplies the increased demand. So this is the vector diagram when the motor is on load. If we increase the more load, then alpha load angle alpha is increases as load angle. The maximum limit for this alpha is 90 degrees. If we increase the alpha, that means increase the alpha. So how we can increase the alpha? When we increase the load. When we increase the load, automatically the angle alpha increases. When it goes beyond 90 degrees, then the magnetic locking between the stator and the rotor poles breaks and the motor comes from the synchronism. That means if the angle alpha increases beyond this 90 degrees, then the magnetic locking between the stator and the rotor poles breaks and the motor comes out of the synchronism. When the motor comes out of the synchronism means the magnetic locking between the stator and the rotor poles is breaks. When it breaks, automatically the motor stops. The synchronous motor is not going to rotate at all. Then the motor stops. So this shows that either the synchronous motor runs at synchronous speed or it will stop. So this is the torque and load angle curve. So where it shows T alpha is maximum when it is 90 degrees. If he increases the above 90 degrees, so if you see up to 90 degrees, the curve as it is showing, as the alpha increases, the torque is progressively increasing. If you increase the angle, if you increase from 30 to 60, simultaneously the torque also increasing. And again, if we increase from 60 to 90 degrees. Then torque also increases and the motor operates smoothly. When the angle reaches 90 degrees, that is the maximum, then what happened? The motor is unable to withstand, unable to operate. It is the when you after reaching angle increasing after 90 degrees, the torque is reducing. The torque reduces here in the graph. The torque reduces and comes to zero. When the torque comes to zero, the motor stops. The torque is this at this instant. The torque is called pull out torque as shown in figure. This is called pull out torque. That is, it comes out of the magnetic locking. That is the attraction of North Pole and the South Pole. It comes out from that magnetic locking. And next, angle of retardation and angle of advance. The angle with which back EMF EB moves from its initial position to give a resultant EMF is called angle of retardation or load angle. So angle of advance is equal to 180 minus angle of retardation. So if you see the analysis where alpha is the load angle, so from this what we understood? So we understood that when the load on the motor is increases, then what happened? The rotor falls back in phase and alpha increases. That means falls back in phase means the axis between the rotor and the stator. Then the alpha is increases. The load angle alpha of the rotor is adjusted to its new value and it produces the torque in the rotor which is sufficient to carry the new load and to supply the losses. If the load is increases further, Then also the alpha increases, then resultant EMF ER increases, then armature current increases, then torque increases. This torque supplies the required torque. But if we increase, if the load increases further, then time comes when no value of alpha can satisfy. That value is 90 degrees. Beyond the 90 degrees, then the motor pulls out of the synchronism and stops. The torque developed at this moment is called pull out torque. That is, it is coming out of from the synchronism. The torque produced at the time of starting, that is at the initial time, is called starting torque. The torque produced during running condition is called running torque or load torque or simple torque. The torque produced when the rotor poles are pulled in the synchronism by stator poles is called pull-in torque. So how many torques we understood now? That is a starting torque, and next one is running torque, and next pull-in torque, and next pull-out torque. So we noticed four torques. What are there? When the motor comes out from the synchronism, at that moment, the torque developed is called pull-out torque. The torque produced at the time of starting is called starting torque. The torque produced during running condition is called running torque or load torque. The torque produced when the poles are pulled into synchronism is called pull-in torque. So these are the four torques. Sometimes he will give for 1 mark also. What is starting torque, running torque, pull-in torque, and pull-out torque. So he will ask in the examination. Next one is analysis of phasor diagram. What is alpha? Alpha is a load angle. And what is armature current? Armature current is equal to ER by ZS. So what is IA? IA is the armature current and ER is the resultant EMF and ZS is the synchronous impedance, which is the combination of armature resistance and synchronous reactance, where resultant EMF ER is equal to square root of V square plus EB square minus 2VEB cos alpha. This comes from the vector diagram. If you add V and EB vectorially, that gives the resultant vector ER. Whereas synchronous impedance is the combination of armature resistance and synchronous reactance. And the angle theta is tan inverse of XS by RA, where XS is equal to synchronous reactance and RA is armature resistance. The angle theta is called internal machine angle or impedance angle. It is constant for motor. So why? Because it is constant, it depends on armature resistance and synchronous reactance. So the significance of theta is IA lags ER, that is armature current lags behind resultant EMF. So this is the vector diagram where it is showing clearly armature current is lagging supply voltage V, where ER is the combination of EB back EMF and V. but practically RA is very small as compared to ZS. So when when we neglect RA, then the angle is 90 degrees. Where this shows the angle between voltage and current is denoted with pi, which is called phase angle between voltage and current, where cos pi is equal to power factor at which motor is working. So this shows the vector diagram where this shows this is the alpha and this is the phase angle, power factor angle, that is between voltage and armature current. And ER is the resultant vector combination of back EMF and supply voltage V. So if you combine these two, we can get ER. So, so what we discussed just now, we have covered synchronous motor, performance of synchronous motor on load, on no load. In no load, again we have two conditions. One is with no losses, another one is with losses. Let us see with no load with no losses. No load and no losses means the synchronous motor is on ideal transformer. If you see in a other motors, where in synchronous motor when we connect to the supply, it will produces a back EMF EB. As we know, in DC motor also back EMF EB is produced, but that depends on the speed. Whereas in synchronous motor, back EMF depends on the speed of the, it is not depends on the speed. Why? Because speed is constant. It depends on the excitation. It depends on the excitation of the synchronous motor, and it is back EMF opposite to the supply voltage. So the voltage across armature is V minus EB, and armature current is equal to armature voltage by armature resistance. So suppose if you take a synchronous motor with no load and no losses, no load and no losses means then what happened? Output is not there, losses is not there. Then the motor is not going to take any input from the supply. This condition of the running of the motor is called floating condition. So that means the both when the motor is on no load, both the supply voltage and back EMF are equal. When both are equal, then what happened? The voltage across armature, what voltage across armature is V minus EB. As both are equal, the resultant voltage across armature is zero. When the armature current is voltage is zero, armature current also zero. Hence, the motor is not going to take any external input from the supply. But in practical, every motor has some losses. So that shows the performance of synchronous motor on load with losses. So when we have the losses, that is the constant losses, that is iron and mechanical losses with small amount of stator copper losses. So because of these losses, previously the supply voltage EB and supply voltage V and EB are opposite and equal. But now the EB falls back by a certain angle, that is called, that is denoted with alpha, and it is called load angle or coupling angle. So this is which shows the rotor and the stator and the rotor poles engagement is not absolutely in the same axis. They are deviated by a small angle alpha. Then if we add these two back EMF EB and V will get a resultant voltage ER, and it draws a supply current, armature current IA, which supplies the losses. So this is no load, no load condition with no load condition with losses. Suppose if we apply the load, then what happened? When we applied the load, the rotor progressively tends to fall back in phase by a angle is called alpha. But it still to continue in the same speed. Why? Because it runs at a synchronous speed. The value of load angle depends on the load of amount. How much amount of load you are apply on the synchronous motor. If you apply more load, there is a more angle of alpha. If you apply less load, the alpha is less. When load angle alpha increases, the resultant voltage ER is increases. When ER is increases, then automatically the armature current increases. When armature current IA increases, it produces more torque. When it produces that this torque will supplies the increased load. Increased load. If we increase the load some more, again load angle alpha increases, the resultant vector ER increases, armature current increases, and it develops more torque, which supplies the increased load. But there is a limitation for this load angle. If the load angle increases beyond 90 degrees, then what happened? The motor comes out of the synchronism and the motor stops. So this torque at this moment, this torque is called pull out torque. That is, the motor comes out of the synchronism. This is called pull out torque. The torque produced at the time of starting is called starting torque. The torque produced during running condition is called running torque or load torque. The torque produced when the rotor poles are pulled into synchronism is called pull-in torque. So we have three types of torques here. That is, what are there? Pull-in torque, pull-out torque, starting torque, and running torque. The torque available at the time of starting is called starting torque. The torque available when the motor comes out of the synchronism is called pull-out torque, and the torque available at the running condition is called running torque. So the input which is given to the motor is called electrical power, that is root 3 VLIL cos pi. From this motor input, if we deduct armature copper losses, then we can get mechanical power developed at the armature. From this, if we deduct iron and friction losses, then we can get output which is available at the shaft. So this shows the motor runs at synchronous speed or the motor will stop. So why? Because the angle which is available at the alpha is it only bear up to 90 degrees. If it is increases beyond 90 degrees, it comes out of the synchronism and the motor stops. So we covered today. What is the topics we covered? Performance of synchronous motor with no load, with no losses. And next is synchronous motor on load, no load with losses. And next one is synchronous motor with load. And we observed on all cases the vector diagram also. Even vector diagram when the motor is on no load with no losses, both supply voltage and the back EMF are equal and opposite to each other. When it has losses with no load, then back EMF is pulled at an angle of alpha. If we increase the load, then what happened? The alpha angle increases more, and which develops the new torque, which is sufficient to bear the new load. So when load increases, alpha increases. That is the load angle increases. When load angle increases, the resultant voltage ER increases. When ER increases, the armature current which is drawn from the armature increases. So this increased armature current will produce us more torque, and this torque supplies the increased load. Increase load. So we covered the vector diagrams in all conditions, both in load and no load, with losses and without losses. You go through all these slides if you have any doubt, and if you have any doubt, ask me in the next class. Okay. Thank you.